Hello friends, welcome to the fourth video on the series of group theory. This video will cover problems under group theory and in particularly the set which are going to be finite in nature. If we have a collection G which has finite number of elements, then how we can prove that a binary operation defined on it is going to be a group or an abelian group or not. So come on, we will move on into the video. The first problem is that you will have to show that the G, which is 1 minus 1 I minus I, is going to be an abelian group under multiplication. The problem can also be stated by the form like show that the fourth roots of unity form a abelian group under multiplication. Okay, so we can say that the problem of the fourth roots are nothing but z power 4 is equal to 1. So what will be the roots taken by z will be 1 minus 1 I minus I. So when we have finite number of elements for my G, so G, which is the non-empty set, consists of finite number of elements, then the problem can be handled in a very efficient way using a table called as Cayley's table. So you call it as Cayley's table. So things will become much clearer when you put it in the format of a table, and the elements will become clear to you as we work out. So what we are going to do over here is the operation which is going to be multiplication is taken in the first box, and now fill your elements in the left as well as in the right. So this makes it as 1 minus 1 I and minus I. Now this becomes 1 minus 1 I and minus I. Now start filling the box using the quantity 1 into 1 is 1, 1 into minus 1 minus 1, 1 into I is I, and 1 into minus I is minus I. Minus 1 into 1 is minus 1, I into 1 is going to be I, minus I times of 1 is going to be minus I. Next, minus 1 into minus 1 is plus 1, minus 1 into I makes it as minus I, minus 1 into minus I, minus into minus plus, and this makes it as I. Now I into minus 1, this is going to be minus I into I know that I square will be equal to minus 1. So this element takes it as minus 1, and I into minus I, so this becomes minus of my I into minus I. So you know that I into I is I square, which is going to be minus 1, but there is already a minus sign that makes it as plus 1. So this becomes plus 1 over here. Next element, minus I into minus 1, minus of minus makes it as plus. So this becomes I minus I into I. Again, we have seen that minus I into I is going to be plus 1, and minus I into minus I, what will be minus I into minus I. We know that I square, I into I is going to be minus 1. This is minus into minus, which makes it as positive. So the resultant is going to be minus 1. So now it is easy for us to find out whether the properties for your group is going to be holding true or not using this table in particularly. So that makes things easy for us. Now coming to the question, what we have been asked to show that it is going to form an abelian group. We need to recollect that the conditions to be satisfied for an abelian group are condition number 1, closure, condition number 2, associativity, and condition number 3, your existence of identity element, and condition number 4 is going to be existence of inverse. This is the 4 condition we will have to show for a group, but we have been asked to show that it is going to be an abelian group. Abelian group is nothing but a commutative group. So the 5th condition we need to include over here is it has to be commutative in nature. So if I am able to show that all these 5 properties are going to hold true, then it will become easy for me to show that it is going to form an abelian group. So that is going to be the task over here. So we will begin with the step 1, which is going to be called as closure. What do you mean by closure? If I take any element a comma b belonging to the set G, the product a dot b must also belong to the set G. Now I see that from this within the table there are going to be just the 4 elements which is going to be a part of the G and nothing more than that extra is present. So whenever I do the binary operation, the answer of the binary operation also belongs to one of the elements in G. Therefore closure is going to be true. How about associative law? I know that multiplication of real numbers is going to be associative in nature. We have seen that in our last problem. So it shows that for any 3 elements A, B and C that belong to G, A into B into C is the same as A into B into C. So you can verify this using an example, but you will have to show it in a very generic way, because one may hold true, the other may not hold true when you have infinite number of cases. But over here, since the elements are finite, you can verify the law for all the quantities over here. So if I am going to take I and minus 1, and this is going to be minus I, so I do the binary operation, I into minus 1, this is I into minus 1 is going to be minus I, and minus I times of minus I times of minus I is going to be minus 1. We'll move the right hand side, A, which is going to be I into minus 1 into minus I. Here it is minus 1 and minus I. Minus 1 into minus I is going to be I. So you make it as I. So next step, it becomes I into I and I into I makes it as minus 1. So I know that associative law is also going to be true. What is going to be the identity element? Identity element is going to be a quantity that satisfies the condition A star E is the same as E star A equal to, it returns back the original element A. So this element is something that acts like a mirror and reflects the element back again. So which element on operation gives you back the same element? We notice that when operating on 1, when you are operating on 1, 1 into 1 is the same 1 into minus 1 is the same minus 1 into I is the same I, and 1 into minus I is the same I. So we find that this element 1 is going to be in such a way that it is going to form the reflection of any element which is going to be taken and gives back the same element. So we conclude that the element which is going to be 1 is going to act as an identity element. So the identity element is going to be E, which is taken as 1. Now coming to the next step, what we want is inverse. I need to find the inverse of each element. What do you mean by inverse? The existence of element called as A inverse, which satisfies the property A star A inverse equals A inverse star A must be giving me my E. So any element, my idea is to find this A inverse, when multiplied with A has to give me E. I take this number 1 and multiplication, I will have to get the answer as E. Where is my answer? My answer is over here. So if I am having my answer to be equal to 1, 1 on multiplying with what gives me 1? 1 on multiplying with 1 gives me 1. So what do you say about the inverse of 1? Inverse of 1 is going to be 1. Now let me check what is the inverse of the element minus 1. Minus 1 when multiplied with what of these element is going to give me 1. So I know that minus 1 when I multiply with minus 1 gives me 1. Okay, so you can go in this way and say that when you have minus 1, you need 1. On multiplying with which number you get it? On multiplying with minus 1 you get it. Next you have an I when multiplied with what element will give me 1? Now this is what we need to check. So move over here. I when it is multiplied by minus I gives me 1. So the inverse of the element I is going to be minus I. Next, coming to the element minus I and multiplying with which of these element is going to give me 1. So now minus I when I multiply it with I gives me 1. So I am able to find out the inverse of each and every element for my G. So I move to say that inverse of 1 is 1, inverse of minus 1 is minus 1, inverse of the element I is going to be minus I, and inverse of the element minus I is going to be I. So I know that existence of inverse is going to be guaranteed. And now comes the last one, which is going to be commutative. For any two elements A and B that belong to your G, I need to show that A star B is the same as B star A. That is, I need to show that A into B is the same as B into A. And we know that for the real numbers or over here under multiplication, the commutative law is going to hold true over here. So when I multiply any two elements over here, say minus 1 into I is going to be minus I into minus 1 is also equal to minus I. So this can be verified from over here in the table, that A star B or A into B is the same as B into A. So we also prove that it is going to be commutative in nature. So this shows that closure, associative, identity, inverse, commutativity, all the 5 holds true for the set of elements 1 minus 1 I minus I under the operation of multiplication. Hence, we conclude that it is going to form an abelian group. Moving on next, we show what is meant by, we are moving to say what is meant by addition modulo n and multiplication modulo n. Addition modulo n is a quantity which we denoted by plus n, and let R be the remainder when you are dividing A plus B by n. And then your addition modulo n, A plus n B, will be A plus B if the value is less than n, and it is the remainder R when you divide A plus B by n when the value becomes more than n. So say suppose I have two elements called as 2 and 3, and I do the operation of addition modulo 4. So 2 plus addition modulo 4, 3 makes it as 5. So I know that 5 is going to be greater than or equal to, my n is going to be equal to 4. So when the number is going to be greater than or equal to n, I need to return the remainder. What is going to be the remainder when 5 is divided by 4? The remainder is going to be 1. So 2 addition modulo 4, 3 will be termed as 1. But rather in the case when I have 2 addition modulo 4 with that of 1, what will be 2 plus 1? 2 plus 1 is going to be 3, which is well less than n, which is going to be 4. So the value is taken as such. So this is what we mean by addition modulo. And the same thing works for multiplication modulo. So R is the remainder when you are dividing the product AB by n. So say take the same element 2 and 3. What will be 2 multiplication modulo 3? What will be 2 3s are? This is going to be 6. So 6 is going to be greater than n. So what happens? Your remainder when 4 divides 6 gives you 2. So 2 will be taken as the multiplication modulo of 2 and 3. When I take the 2 multiplication modulo 1, 2 1s are 2. 2 is going to be well less than n. So it is taken to be the same 2 itself. So this is what we mean by addition modulo n and multiplication modulo n. Now moving on to the next problem, we have prove that the set G, which is the set of 0, 1, 2, 3, 4, 5, is a finite abelian group under addition modulo 6. Why we have only 5 or 0 to 5 over here present? Because when we take any addition of two elements and divide by the element called as 6, the possible remainders that will be left will only be 0, 1, 2, 3, 4, 5. If it is going to be more than 6, it divides one more time and it gives a remainder of 0 again. So the possible remainders for me will only be between 0 to 5. Now let me form the table over here with the class. This is going to be addition modulo 6. So you write it as plus 6. Addition modulo 6. You have class 0, 1, 2, 3, 4, 5 and 0, 1, 2, 3, 4, 5. Now you can see that 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 3, 4 and 0 plus 5 is going to be 5. This is well less than 6, so it will be the same. Again you can fill this column. 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, 4 plus 0 is 4, 5 plus 0 is 5. Next coming 1 plus 1 is 2, 2 is less than 6, 1 plus 2 is 3, 3 is less than 6, 1 plus 3 is 4, 4 is less than 6, 1 plus 4 is going to be 5 which is less than 6, 1 plus 5 is going to be 6, 6 is going to be greater than or equal to. So what you'll have to do, divide 6 by 6, what is going to be the remainder? It leaves the remainder 0. So you place the remainder 0 over here. 2 plus 1 is going to be 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is going to be 6. So 6 divided by 6, remainder is 0. Now next number 2 plus 5. 2 addition modulo 6 with respect to 5. 5, 6, 7. So 7 you divide by 6. What is the remainder it leaves? It leaves a remainder of 1. So place your 1 over here. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 6. So that becomes 0. 3 plus 4 is 7. So that becomes 1. And 3 plus 5 is going to be 8. 8 on divided by 6 leaves you a remainder 2. So that makes it as 2. 4 plus 1 is 5, 4 plus 2 is going to be 6, so that becomes 0, 5, 4, 1, 2, 3. 5 plus 1 is going to be 6, so 0, 1, 2, 3, 4. So now my Cayley table is ready. The thing which we need to show that it is going to be abelian. What do you mean by abelian? I need to satisfy the criterias of closure. Next is going to be associative. Next I need to show that it is going to have identity element. Next I need to show that it has an inverse, and since it is going to be abelian, I also need to further show that it is going to be commutative. Right, you take any two elements over here and do the addition modulo 6. Do you get any other number apart from the element which is present in G? No. So I can show that very clearly from the table. A star B belongs to G whenever you have A and B that belongs to G. So closure is going to be true. What is going to be associative law? Associative law is nothing but taking three elements, A addition modulo. So this is the addition modulo 6 operation which we are doing. A addition modulo 6, B addition modulo 6 with C is the same as A addition modulo 6 with B, and then addition modulo 6 with C. You can just verify this by placing any of the elements over here. 3, 4, 5. So 3, 4, 5. Okay. So go for 4 plus 5. What is 4 plus 5? 4, 5. The answer is going to be 3. And now go for 3 plus 3. What was going to be 3 plus 3? It's going to be 0. Now check the other way around. What is going to be 3 plus 4? 3 and 4 makes it as 1. And 1 plus 5, 1 and 5 makes it as 0. So you have both the sides to be 0, and you can say that associative law is going to be true. Next comes the identity element. Which element on taking returns back to you the same element? Now I take 0, I get back 0. I take 1, I get back 1. I take 2, I get back 2. So this element 0 is in such a way that it gives you back the same elements when operated with it. So I can conclude that the identity element over here is going to be my 0. Now moving on to inverse. So what is going to be the inverse of an element? Inverse of an element is in such a way that A star A inverse must give me the value of E. And what is my E? E is going to be 0. For every A, I need to find this A inverse that gives me 0. So block your 0. Where is your 0 over here? My 0 over here is here. Okay, so what is the element that gives me 0? 0's inverse is 0. When I take 1 over here, 1 multiplied with what will give me 0? Now move 1 with what gives you 0? 5 gives you 0. So what is the inverse of the element 5? Inverse of your element 1 is going to be 5. Inverse of your element 0 is going to be 0. Now take 2 over here. 2 into what is going to give you 0? So where is your 0? Your 0 is over here. 2 multiplied, sorry, addition modulo with 4 gives you 0. So what is going to be the inverse of your 2? Inverse of 2 is going to be 4. Next, 3 with what gives you 0? 3 with respect to 3 gives you 0. So inverse of 3 is 3. 4 with what gives you 0? 4 with 2 gives me 0. So inverse of the element 4 is going to be 2. And 5 with what gives me 0? 5 with 1 gives me 0. So inverse of the element 5 is going to be 1. So I have now shown that all the elements possesses inverse. And furthermore, commutative law is nothing but I can show that A star B is the same as B star A. So 4 addition modulo 2 is going to be 0. What is 2 addition modulo 4? That is also going to be equal to 0. 5 addition modulo 3 is going to be 2. What is 3 addition modulo 5? That is also equal to 2. Now that can also be verified in a way like the diagonal line you plot. Above the diagonal and below the diagonal, the elements are going to be one and the same, which means the matrix over here is going to be symmetric in nature. If it is symmetric, then commutative law will automatically be true for you. And so what we have proved, all the 5 properties are true. Therefore, the addition modulo 6 operation forms an abelian group under for the set G1, 0, 1, 2, 3, 4, 5. I hope for the finite set, the concept of creating the Cayley table and then verifying the related laws according to us whether it is a group or an abelian group can be done now easily after watching this video. I hope you enjoyed the video. Happy learning. Keep learning.